My name is Levi Zitting. I'm an engineering manager at Midwestern Interactive. And I'm here today to talk all about the Meadow board and its place in IoT. And I'll kind of talk a little bit about what IoT is as well. I got a really cool demo planned. It might not work. We'll see. It didn't work just before it. I might have to have everyone turn their Wi-Fi off on their phone and we'll try it. But I did record it ahead of time. So we got some backups just in case. So to get started, let's first talk about what IoT actually is. Who here has heard the term IoT before? Okay, there's a few hands that didn't go up, so I'm just going to kind of explain it really quick. So IoT stands for Internet of Things, which basically means it's internet connected physical devices. And you kind of see these cropping up everywhere, right? You have the Google Home, the Alexa, you have smart fridges, you have smart toasters. I feel like I saw one of those the other day, which is a little crazy. And these number of connected devices is getting larger and larger, and they're also getting cheaper to manufacture. It's really cheap these days to get a low power device connected to the internet. And so it's kind of like bringing in this whole new world of possibilities in what we can actually build. And specifically, it's kind of all about bridging the gap between the physical and digital worlds, right? Your Google Home is connected to all your digital Google account stuff, but it's also got a physical presence in your house with a speaker and can control other devices and those kinds of things. One kind of from an ideological standpoint, potentially, it's also kind of I like to consider it the latest revolution in software development. So if we kind of think back over the history of this industry, we had the web, right? This was this huge revolution in how developers shipped software to users, right? And then we also had mobile development become another major revolution in the industry as well, where now everyone has a really powerful computer in their pocket, and that introduces a whole new array of software solutions. And so IoT is kind of another one of those revolutions, in my opinion, where now we're introducing a whole new set of capabilities that users didn't have before, and it's changing how we think about software and what it's capable of and all those kinds of things. So what is Meadow? So Meadow is a microcontroller, and it's a microcontroller made by this company called Wilderness Labs. And I have a couple of them up here. I'm going to pass this one around. You all can take a look at it. Just make sure I get it back before the session's finished. So I'm going to start over here, and if you guys can just pass this down through the rows, take a look at what's on there and that kind of thing. So what's a microcontroller? A microcontroller is essentially a small computer that can be incredibly power efficient. It's got all the basic components that are in your laptop, just toned way down so that they can sip battery power instead of needing charged every day like your laptop might need to be. And there's a ton of these microcontrollers out on the market. You have Arduino is a company that makes a whole bunch of these kinds of things. There's also, some of you might have heard of the Raspberry Pi. The Raspberry Pi I wouldn't necessarily consider a microcontroller. It's kind of more of a general purpose computer. It can sip power, but generally it can do way more than just a microcontroller can. And where microcontrollers really shine is in kind of a larger electronic project. They're the brains of the operation. There's going to be something like this in any of those smart devices that I just talked about, right? A fridge is going to have one, maybe even more of these kinds of things to control all sorts of features about that smart fridge, right? The Google Assistant, or the Google Home in your house is going to have one of those in there as well, probably a little bit more powerful, but you get the idea. It's the brains of the operation of some IoT device. Now there's, like I said, there's a ton of these. There's a few things that set this board in particular apart from others. Probably the biggest is that the application code that you deploy to this thing and run on its processor and stuff is written in .NET, which is a little bit unique. A lot of these microcontrollers, the code that you write is in C or C++, with a few kind of niche ones out there that have capabilities in higher level languages like Python or JavaScript or those kinds of things. And this is, to some extent, the colloquial .NET version of how to do IoT projects. Another thing that I was really impressed about as I was kind of digging into this platform is they also have this huge library of drivers for talking to other hardware. So this little board, which I'm going to pull up this camera here so you guys can kind of see it in action. This is the other one that I have here. This board, it's got all these little pins, and I'll talk more about those pins in a minute, and they can be connected to all sorts of different hardware devices. I have like a large list of the different types, but what's really cool about Meadow and this platform that they've built on top of .NET is they have ready-to-go drivers for most of these devices, where you can just worry about your high-level business logic, if you will, about your IoT project, and not have to worry about the low-level details of what signals to send or receive from that device. So there's actually two versions of this board. So we have the one on the left here, it's called the F7 V2 Feather. And to break that name apart a little bit, F7 actually comes from the name of the main processor that's on it. I'll talk more about that in a second. This is the second iteration of this board. They had a V1 that I believe was like a Kickstarter project early on. And they've since kind of like revamped it and added some better specs to it and more features. And the Feather naming scheme comes from the shape of this board. It's actually a standardized shape. There's a company called Adafruit that makes all sorts of additional hardware devices that connect with a board of this shape with somewhat of these pin layouts. And so that's what the Feather part of this means, is that it matches that form factor. But then for more, like the F7 V2 Feather is really meant for development purposes. It's great to plug into a breadboard, which that's what this little guy is, this little white thing. This is what we call a breadboard, and it's used for putting together electrical circuits without having to do any soldering. A bunch of these little pins on here are actually connected as if they were soldered, right? And so the Feather format works really well with plugging into a breadboard like this, but it's not really great for production type scenarios. And so that's why they created this core compute module that is meant to sit inside some carrier board. It's got all the same basic components on there, all the same chips. It's just got a different connector on the outside that's a lot more compact and ready for production, if you will. Let's talk about the specs on this thing. So there's a lot of numbers here. I mainly want to add this to kind of like give you an idea about just how like low power this kind of thing is. So the main CPU on this board is called the STM32F7. Like I said, that's where the F7 in the name of the board actually comes from. And this is a single core ARM-based CPU. And specifically, it's only a 32-bit CPU. That's what the 32 means in there. And it runs at 216 megahertz. Now, I'm not sure if like that means anything to some people in this room, but your typical laptop is going to run at like 2 or 3 gigahertz, and it's going to have like 8 cores or something along those lines. This is like a minuscule fraction of that capability, because the goal is not to crank through benchmarks and a lot of data. It's to like be really efficient about how much power it actually draws from potentially a battery or some other direct power source. What is really interesting about it and kind of sets it apart from other STM32 chips, because it's a popular processor to put on a lot of microcontrollers, is it has the ability to do 2D graphics and process JPEGs. It has like hardware acceleration for those kinds of things. Traditionally, those are things that a general purpose CPU is actually really bad at doing. And so they have specific hardware in there to make those things run faster. So if you, I talk about this in a minute, but you can connect an LCD display to this thing and put some images on there. And that's possible because of those accelerators. It also only has 32 megabytes of RAM, which is a little insane to think about. My laptop here has like 64 gigabytes, several, like an order of magnitude and then some larger. So it's a very minuscule amount of RAM. And then 64 megabytes of flash storage, so that's readable and writable. In some instances, on some microcontrollers, there might not be any storage at all, other than read-only memory that your program gets stored on. In this case, you can actually like read and write files to this device, which is interesting. And then kind of the other big aspect of this is it does have a coprocessor sitting on the board called the ESP32, and that coprocessor manages all of the Wi-Fi and Bluetooth capabilities, because this thing can connect to Wi-Fi networks and to a Bluetooth server. And none of the low-level details and the processing that goes there bogs down your main application code. Instead, that's all handed off to this coprocessor. And the main STM chip is just going to send some commands back and forth to get information or to tell it to do something, that kind of thing. This right here is a pin layout of this board. There's a lot of stuff here that honestly I don't even understand. I'm not a hardware guy, to be clear. I'm much more on the software side of things. So there's a lot of these things that you really don't have to care about necessarily unless you're trying to get into some really specific scenarios. But I'll kind of give the highlights here. So up at the top of this board is a micro USB port. And that micro USB port is used to both power the board and to connect it to a computer to load programs onto it. So it's also a data connection. This little white section here on the edge, the right side here, this is, they call it a JST connector, but it's for connecting a battery. It's a standard battery connector. Did I bring the batteries? Nope, I left those at home. I had some batteries here, and those connect right into that thing. There's also some there's another pin here labeled battery, which is kind of interesting. And it's because you can actually like wire a solar panel into this board, and that solar panel will both power the board and charge the battery if it's low. So you can actually have multiple power sources coming together to keep this thing alive for a really, really long time. Some other really important pins, we have this ground pin. So in an electrical circuit, everything's got to make a big loop. And so every circuit will come back to that ground pin. We also have this 3.3 volt and 5 volt pin. Those just constantly supply power at those specific voltages. So you can wire them directly into an LED and it'll be powered all the time or something along those lines. The rest of these are where the interesting things start to happen. So the one I'll explain first is these analog inputs. So these are pins that are meant to read a voltage that's applied to the pin. And this is useful for a whole bunch of different types of sensors. If we have something like, say, a temperature sensor, that temperature sensor in many cases will encode the current temperature as a voltage. And so we're reading an analog signal from that device and then turning it into something digital in our program. And so there's a handful of these for both, I believe they can also do analog output in some instances where things like speakers, those are gonna need analog output because you're sending like pulses of certain voltages to push the speaker membrane back and forth and create vibrations in the air, right? There's also this PWM timer group. PWM stands for pulse width modulation. It's a really wordy term. But basically it's the ability for that pin to send out just pulses of electricity really quickly, which you use to power like dimmable LEDs. So an LED that can vary its brightness. You'll use little bursts of power spaced so far apart to control the brightness of that LED. And so there's a whole bunch of pins on here that support that functionality. And then kind of the last one, the most popular one in here, the most popular type, is the interrupt pins. And interrupt pins are really interesting in that they can basically raise events to the main chip. So when a voltage goes from 0 to 5 or something on one of those pins, the CPU can be notified about that. And it doesn't have to continually check the state of power on that pin. It can instead have like this event-driven system, which is much more power efficient. There's a ton of other like more complex versions of pins in here that have specific capabilities. For the most part, these are for talking to really specific types of devices. So you might have some device that connects to, I don't know, like this SPI port, these SPI pins. I have no idea what SPI actually is, but there's some device that's gonna need to communicate over a certain protocol. It's gonna expect signals coming in a certain format and maybe like certain voltages even. And so the Wilderness Labs team has ensured that these pins conform to those protocols if you need to hook that kind of device up to this thing. Then down at the bottom, we have a reset switch and a boot switch. So reset is fairly straightforward. It just like powers the device off and turns it right back on. Boot is for putting the device into what we call DFU mode or device firmware update mode, and it's for wiping the device with a new operating system. More on that in just a second. Oh wait, actually right now. So, so let's talk about the software side, which is the part that I kind of nerd out about a little bit. So first and foremost, this board does have an operating system. So there's an operating system deployed to this thing. It's called Meadow OS, and it's made by the Wilderness Labs team. And it is what we call a RTOS, or a real-time operating system. It's based on one called NutX, which is it's managed by the Apache Foundation. So they forked it, made some modifications to it, and called it Meadow OS. And RTOSes are a unique type of operating system. They're not nearly as general purpose as something like Windows or Linux. They tend to be much more narrow in scope so that they can run on a low power, low hardware device like this. So they forego a lot of things that you might be used to in an operating system, like the concept of users, right? Or in some cases, maybe even like a file system on some of them. Like you might just deploy, raw binary data that's supposed to be executed by the chip. And then they don't even really necessarily have the concept of applications. Normally they have like one. And the kind of whole point of an RTOS is that they can take a single core chip like this that doesn't have any parallel computing capabilities and kind of fake it by letting programs take turns executing on that chip, while still ensuring that they respond to things like interrupts in an extremely timely manner, which is important in a microcontroller-like instance where you need to respond to events super, super quickly. So in that, the Meadow OS, it does have somewhat of a file system. It's pretty limited, but like I said, it doesn't have user accounts, and it doesn't really have the concept of an application other than the main one that you deploy to it. So the next stage in kind of this software stack, if you will, these layers, is the Mono runtime. And so if you're not familiar with .NET history very much, Mono was a re-implementation of the .NET runtime, like the thing that is built into Windows. It was a re-implementation of that supported ARM-based CPUs. And I believe it was originally created to power the Xamarin framework, which is the ability to use .NET to write mobile applications. And so when that, this initial version of Mono was created, they were presented with a whole bunch of new restrictions that they had to solve for, like the fact that it was on ARM and only 32-bit, and that there was not going to be a lot of memory available because mobile devices, when this was originally made, certainly didn't have a ton of memory. And so honestly, a lot of the optimizations that make running .NET on something like this possible, they were kind of already done when Xamarin was built. And so the Meadow OS and their SDK essentially just reuses all that work. So the Mono runtime is what makes all of this kind of possible because it's really small and really efficient. And then there's kind of two really important libraries that are built into their SDK that also make the rest of this possible. You have the Meadow.core library, and this is essentially their hardware API. So if there's going to be any talking to some piece of hardware, you use this Meadow.core library. And then on top of that, kind of at the highest level of abstraction in this software stack, is Meadow Foundation, which is that driver library. So it's got all of those, it's got these drivers for all these different types of devices. So what kind of stuff can you do with this thing? I talked a lot of specs. I've talked a lot about like the software stuff. What kind of things can you build with it? To start, let's talk about the kind of devices that you can connect to it. So this, in no particular order, is like a long list of a bunch of these. And these are all devices that I could find one or more drivers of on their, in their Meadow Foundation library. So keyboards, keypads, simple buttons. If we go to this one, we're going to be using just a simple button for the demo here. General joysticks and getting like, the angles and all that kind of stuff. They also support just a bunch of like controllers. I think there was some drivers that could connect to like a Wii controller and get input from a Wii controller. From an output perspective, you also have things like LEDs. There's actually a built-in one onto the board. I forgot to show that in the pinout, but there's an RGB LED, which is what's blinking right here. You can connect displays to it, and that's where those 2D graphics libraries come in handy. You can connect speakers, you can connect some simple cameras, a wide range of sensors. You can detect temperature, motion, the brightness in the room, those kinds of things. And then, of course, you can also control servos or motors with this. Most of the time, if you're controlling a motor, you'd use what we call a relay. And a relay is a way for a small electronic circuit that doesn't have a lot of power associated with it to turn on or off a much higher power circuit to drive a motor, right? And also there's like the ability to connect GPS devices and collect GPS data through this thing as well. So This is by no means the definitive list. There's probably like 100-something different drivers on their website when you look through the Meadow Foundation library. These are just kind of some of the highlights. They also have like a whole bunch of projects that they have tutorials written that you can go through that walk you step by step on building all these things. So I've grabbed like some really cool ones. This one is a Simon Says game where you like make sure to follow the pattern that the board decides by having an LED and buttons next to it, and then a speaker that will say a sound if like you got it incorrectly. This one is just a simple little dial that its input is directly connected to the output of that servo. And that's all done in software. It's not like wired directly up to the servo. If you can see, it goes into the board processes that input and then sends it as output to that other thing. So kind of like a remote control, if you will. And then we also have, this is kind of that LCD display. So this button press will go talk to a weather API, fetch some weather data, and then display it on this little LCD screen. And then I really like this one because it had a lot of cool wires and blinking lights, and I love that. But like an LED dice roll. These little titles down below here, these are links to those tutorials. So if you want to find these slides afterwards, they'll be at slides.levizitting.com, and you can go follow the links and go through some of these things if you pick one of these boards up. One more thing I forgot to mention before we jump into the demo about this board is it's $45. So they sell them on their store, their Shopify store. They're $45, which is kind of pricey. They do have enterprise pricing that they don't share. So I imagine that if you're trying to do a really large scale project and ship a whole bunch of pieces of hardware, they likely will come down on price. Also, when you order it, there's 2 different ways to get these pins pre-installed. So that one that I sent around, it had pins pointing down to go into the breadboard. Those pins, when you order it normally, they are not pre-installed at all, and you're expected to go solder them into these little holes that are on the board. For an extra $5, they will put those pins on. And there's 2 versions. There's the version that point down and stab into the breadboard, like I have here. And then there's also the ones that you see in these pictures where they show up as female inputs on the board so that you can have things coming out of the board, which works really well if you have they ship this little wooden plate to mount the board into. I didn't realize that when I ordered it, so I got the other version, so that's why mine doesn't look as pretty as theirs. But they will solder it on for you if you don't have the right soldering equipment and stuff like that. Before I jump into the demo, are there any quick questions? Yes, in the back. What's that?
Do you know what the sleep current is when you put it to sleep?
That's a good question. I don't know what the actual current it draws in. I will say that the sleep mode functionality is fairly limited right now. So that's kind of a major selling point of an RTOS, is that the device can actually go to sleep until it's woken up by something. Currently, they only support time-based sleep. So they do not yet have support for a button press to interrupt the system and wake it up. I know that it is on their roadmap. There's a bunch of cool stuff that they have in there, and one of them was that thing. I think we had another question.
Yeah, how's the battery life?
It's a good question. The biggest thing is it depends on the battery, obviously. I haven't done any measurements with it, so I couldn't really tell you. And also, it depends on if you're going to use that sleep mode or not, right? So I don't really have any numbers to share in terms of battery life because I haven't really tested it. The main thing, they do have a hardware API or not a hardware API, but they do have methods to go like get battery information at runtime, and it'll give you like an estimated how long until the battery runs out sort of thing. I haven't even tried it yet, so I couldn't tell you. Good question though. Any others? Yes?
For the core and foundation, are those open source libraries?
Great question. Yes. So most of their software stack is open source with the exception of the internals of Meadow OS. Meadow OS is not written in .NET, to be clear. It's a fork of NutX, like I talked about, which is open source. So most of that's like some real low-level implementation. It's also got a lot of like really specific stuff in there to this hardware configuration, more than likely, and they don't open source that, but the core and the foundation libraries are completely open source, as well as I think their command line tools and their main SDK and templates and all those kinds of things. Okay. All right. So for a demo, this probably won't work. I've tried it a few times just before we set up. I think the problem is that this demo requires the board to connect to Wi-Fi to do some stuff, and there's a lot of Wi-Fi devices around right now, and that could be causing some interference and having it not connect. So instead of even trying, I'm just going to show the pre-recorded video that I took, which all the code for this is linked off in these slides, as well as this demo video. And I'll just kind of explain what's happening as it's playing. So first off, this might be kind of hard to see, but this is a string of commands to go deploy an application to this thing. So the first step is I build my .NET project using the standard .NET CLI. And then after that's finished, I use the Meadow CLI, which I haven't talked about yet. It is a .NET tool, which means you use the .NET CLI to install the Meadow CLI. Excuse me. And then there's a whole bunch of commands in there, including commands to flash the OS to the device. So that's a kind of prerequisite that I haven't talked about yet. The first step that you have to go through when you're ready to use this thing is you have to put it into that DFU mode, device firmware update mode, and you have to run a flash command to load the OS onto it. From there, I can deploy my app. So Meadow app deploy, and then I'm pointing at a file in my .NET output, specifically this app.dll, and that will copy that file to the device, as well as any dependencies that it has, and then it will start executing it. Now, one thing that's kind of interesting is that command will copy things over and then exit, and so we string one more command at the end to listen to log output. So this listen command will keep my terminal open until it's finished. So while that runs, this does take a few minutes. This is like very low-end hardware with low amounts of storage. So even though these are pretty tiny files it's copying over, this whole process of the demo takes like 2.5 minutes. And with a bunch of that being like copying. So right here, it's checking to see which of all the various assemblies, which are, the .NET compiled output, which of those assemblies does it actually need to copy over to the device? Because it only tries to copy what's changed, given how slow everything is. While this is running, I also want to kind of give a highlight or an outline of the circuit here. In fact, I'm going to pause this video and go to the live camera since it's a little bit bigger. So this might be kind of hard to see. There's only a few wires involved. So over on the left-hand side, I have a wire coming out of the ground pin, and it is being put onto this column of pins. Those far left two columns, they are vertically all connected. And so there's actually a little minus symbol right over here to try and point you in the right direction and have you connect that to ground. So that whole column is ground, and then I copy it over to the other breadboard using a couple other jumper wires. So that means that kind of middle column right here, this little guy, is all ground as well. And then I have another wire coming out of the D10 pin, which kind of just an arbitrary one that I chose, and that is wired into this button. So this button does create a full loop when I push it down by connecting the D10 pin to ground. Okay. Okay. So this is finished deploying to the board, and now it's currently waiting for the application to start up. And while it's doing that, I should also tell you what exactly we're demoing. So in the description, I've talked about turning your mailbox into a smart mailbox. And so the concept is this push button, which I also left the one that I would use in production. There's another version of a switch that works really well against a door. And so that switch would replace this one on this circuit. And then I would have the whole thing powered by a battery sitting in my mailbox. And with the idea being that as soon as the door opens, the device would wake up and actually send me a text message saying that my mailbox was opened. And it does that by connecting to my Wi-Fi network and using the Twilio API to deliver a message. And it just does that all directly from the device. So that's what we're about to see in this demo. Right now, it is actually connecting to Wi-Fi. You can see that down in the logs below. And another kind of thing that I did is I made it possible to control that LED at any given time. And so that LED will blink blue when it's connecting to Wi-Fi, but it will blink a different color when it's doing a different type of work. Okay, so I just pushed the button and it actually detected it. It can detect an open versus a close. It should say close in just a minute. The logs are a little delayed given that it's trying to do a lot of things with not a lot of resources. So it just opened and closed it, and in a second here, my phone is sitting next to this guy, and it will get a text message. I'm standing here like wondering if it's going to work, even though I pre-recorded this, and it definitely works. It does take a little bit to send because it's busy doing stuff. It takes a little bit for it to start up and do all the things. But there we got a text message, and it's actually delivering one more. It won't show up in the notifications. But that one more, let me go back. That one more is like the close message. So there's an open message and a close. And the LED was also blinking green. That was some programming logic I added in there where when the LED is when the device is delivering a text message, blink green. So I have full control over that LED. I can do whatever I want. If I actually go to the device right now, it's blinking blue because it's attempting to connect to Wi-Fi, but it didn't work. So the last part of the demo, and this would not really be useful in the mailbox setting where like the goal is low power usage. One thing I was particularly impressed with, and I haven't really talked about, is this board has the ability to run a web server on the board. And so when it's connected to Wi-Fi, you can like have it host a website or host an API. So what I've done is I have it running a web server, and as the button gets pressed and unpressed, it saves in a log file all of those events. And then I have an endpoint that I can go call to get all of those events from another device. So I can just like at any point over the network connect to this thing and say, hey, what's happened on this if maybe something goes wrong with text messages. Or that could also be a system that like keeps track of the events in case there isn't internet connectivity, and then when there is, again, try delivering all those text messages. So this last part of the demo is the device is still running, and I go over to Postman, which lets me make requests, and that right there is the IP address and the endpoint for this specific getting these logs. And it also does take a little bit. It's slow, like I said, but right there we have, let's go back. There we go. I ended the recording too soon. Right there we have some JSON data that represents all the logs from this thing. So that's kind of the demo here. One thing I want to go show off really quick is what does the code look like? What does it look like to actually write code in this thing? Show of hands, who's written .NET code before and is kind of going to understand what we're looking at in here? Okay. If anyone does have any questions or if there's like some syntax that doesn't make sense and needs some more explanation, feel free to call it out. I'm happy to dive into it. So this right here is that's the wrong keyboard shortcut. So this is our project directory structure, and everything starts in this Meadow app.cs file. And specifically, the file name doesn't matter here, and the class that's in this file doesn't matter either. It is the fact that it inherits from this base app class. That is what defines an entry point in Meadow. So like when the app starts, it'll look for a class that inherits from app, and it will instantiate it and start calling some lifecycle methods on it. One thing that's really interesting and really powerful is to this app base class, we actually pass a generic parameter, and this parameter is supposed to represent the device that you have, the device that this app is going to be running on. And what that actually gives you is really strong type safety about all the capabilities of this device. So ignore the rest of this code. I'm going to kind of show what I mean there. This app has a device property, and there's a pins property on there. And right here, because I said F7 Feather v2, there is a list of all the various pins on here. And it's aware of that from a type layer. Like if I try and use a pin that doesn't exist, I'm going to get a compiler error instead of like a runtime error, which is really, really cool. So in this app, there's kind of two main lifecycle methods at play here. You have this initialize, which you use to do a bunch of setup, and then you have run that should like kickstart the main execution of your program. And so the first thing that I do in initialize here is I have this register services method. So if you've never used .NET before, that whole ecosystem is really big on using what we call IoT containers, and they're basically these they're managers of all of the instances of your various classes in your program. So you register an instance of a class in there, and then it's really easy to get that instance back at any point in the program. And so right here, I'm registering a bunch of those classes so that I can just grab them later. And this is kind of like a really interesting pattern. It's something that .NET in particular is especially good about because it has a lot of what we call runtime reflection, where you're able to write code that inspects the code itself and do some interesting logic about it. So after we register all these services, we then grab a couple and store them as properties because we're going to need to access them later. And then we start initializing things. The first thing we do is I have this storage service that loads and writes to that log file, and I initialize it to kind of like pre-populate a cache of all those logs. And then I have a Wi-Fi service that has all of the details to connect to a Wi-Fi network. And so I have that connect. And it actually is going to wait for both of those things to finish before moving on to the next thing, where the web server service gets initialized. And then the last thing we do is I have this mailbox button service that detects the button presses, and I start listening for those events. Which is kind of where the most interesting aspects of the program actually are. Does anyone know what the time I was supposed to end at? I don't want to go too long. Okay, all right, we're doing okay. So this mailbox button service, right here, this is the constructor for it, and this is the IOC container in action. So in the constructor, I just specify the classes that I need access to, and that IOC container is going to take care of giving them to me, and I don't have to like manually instantiate even this class and provide it all that information. So I grab a couple other services, a logger, this SMS queuing service. One thing I didn't talk about is I implemented a queue so that every time the button gets pressed, it adds an event into a queue so that the SMS messages are always sent in order and it doesn't try and like overload itself by sending too many at once. And then the storage service is also used in here. This next line and the lines below it are kind of like the interesting hardware parts. So right here, I instantiate this push button class. And this push button class, all I have to tell it is what pin my button is connected to. And once I do that, I can simply just add an event listener. So this right here is what in C# we call an event delegate. So we're adding an event listener that will be called automatically. This callback will run whenever a press of the button gets started. And then there's another one for when it's ended. And that's it. That's all of the code you have to write to interact with hardware stuff here. And what's really cool is I mentioned that not all those pins are interrupt pins. Some of them don't have that capability for the system to be woken up and have an event raised. This push button class takes care of doing what we call polling, where there's an infinite loop that's just checking it every few milliseconds. This push button class can actually detect if the pin that we specify has the capability to do interrupts, and if it doesn't, it will fall back automatically to that polling, and we don't have to care as the developer. They've just implemented all those little low-level details for us, which is really, really powerful. There's almost no code in here that actually talks to hardware, and that's because there's not a lot of hardware stuff going on here, admittedly, but even when there is, it's very intuitive and not complicated. And that's kind of where I think the power of this platform really comes about. It's not just the fact that it runs .NET, and I love .NET. It's the fact that they've built these really good abstractions over the hardware so that you can focus on the intricacies of your specific problem and not the intricacies of talking to hardware. One thing I want to do really fast is just go to their website and go to, they have a little page where they show off a couple more of these. Let's see. So this right here, so this is some code that talks to this servo. So and this is actually more complicated than it is these days. They've actually simplified the API and they just haven't updated their website. We create a new instance of a servo. We're essentially just specifying the pin, and then I believe that last part is the model of servo, so that it knows the details about, because they've written that code for you. And then you create a push button, and on click, you just say rotate to this degree or rotate to this degree. You don't have to worry about oh, am I sending the right voltage to this thing and the right amount of power, and are the timings correct, or any of those kind of things. They manage all that and just give you this really intuitive API. This is doing analog joystick stuff. There's obviously none of the LED buttons, but the joystick is connected to these sets of pins, and they then give you a get position method to just get an object that represents the position of this thing. And I can't remember if the last one was really cool or not. Oh yeah, an LED bar graph. Just more interesting hardware with like really simple, intuitive APIs that aren't overly complex and get rid of the boring details for you. So that's my overview of this Meadow board. Are there any other questions about all the stuff that I went over? Okay. Well, if anyone does have any questions afterwards, I'm going to be here at the conference the rest of the day, and I'm happy to talk about this stuff more. But thank you all for making it to this thing and spending some time with me and getting to check out this cool thing. So thank you.